Hello everyone, welcome to CYBR708, and this is Sage Modeler System Modeling Tool Lab. And we're going to be doing two labs, a smaller one and a bigger one, kind of like Loopy, where we worked on just kind of some basic relationships and creating a simple simulation, and then we went into creating a growth model. In this one, we're actually going to create a kind of an interesting, a fun one. At least I think it's fun anyway. We'll create a simple one that shows the relationships and how the tool works, but then we'll also create something that's a little bit more dynamic as per our coursework dictates. And so the first thing we're going to do is jump out to the internet and get Sage Modeler up and running. Just type in Sage Modeler, and you can go Systems Modeling Tool right here and then launch Sage Modeler. And it's created by MIT. It's actually a really neat online tool, and it's pretty powerful. It can do quite a few things. But you can open up and browse examples. Feel free to do that at another time. But right now, I'm going to actually create a new document, and we're going to get a blank space. And so you'll notice this is very much similar to like Loopy, in the sense of I've got a canvas, I've got an open area, I've got some icons, and so it's pretty straightforward. So the first thing you need to do is up in the upper left hand corner, is you're going to drag down an object, and this is a node. And our first one we're going to do is I want to show the relationship between between two nodes and how they can be connected. So what you'll do is you're going to drag in two, and then this line up here you're going to drag over here, and then I'm going to be able to create some a relationship. So to do this, I'm going to call this I'm just going to call it variable. So you double click it down here and just start typing variable. And then over here you can do the same thing, variable B. I guess we should probably be more explanatory. Variable A and variable B. Okay, so then once you've got that variable A and variable B set up, then double click variable A, just like double click it, and then you'll get this effects, affected by, and all this fun stuff that shows up on the right hand corner here. And what you'll want to do is take note of all the different things here. So, but more importantly, I've got this brush, I've got this ruler, I've got the settings, and I will show those in just a second. But more importantly, I want you to take notice of this language here. So I'm going to create a relationship between A and B. So an increase in variable A causes variable B to do what? So the first thing I want you to see is that I want it to increase. So whenever A increases, I'm going to say by the same here. So I can say to increase by about the same, a lot, a little more, and less. So I'm going to say about the same. So I'm going to make it a linear relationship. So this is what we call a positive relationship. So as A grows, B is going to grow. So then what we're going to do now is I'm gonna hit this simulate button, and then what happens is I've got these sliders. And so what happens is when I slide, so it's a proportional growth. So when A grows, so does B grow. When A decreases, so does B decreases. So that's it. It's pretty straightforward. Now I can change the relationship by double clicking variable A, and then I can go in and make an inverse relationship. I can make a decrease. So then I'm going to save that. And so what happens is when A decreases, B increases. When A increases, B decreases. Right? I got this opposite effect. Now I can actually do, and this is similar to Loopy in that regard. But there's actually something that I can do that's different than Loopy, in the sense that I have more control. You can see I can do a lot, a little, more or less. So if I do like a little, like decreases by a little, it's going to put a limit on it. So what happens is, you see I'm going to go variable A. It doesn't go all the way to the top. It's kind of like the inner quartile. it does the average plus or minus. It does a 50 plus or minus 25% from the middle. So if I go down, it goes up to 75%. If I go up, and then it goes to 25%. It's a pretty straightforward algorithm they've built into this. It's pretty neat in that regard. I can also go polynomial. So I can do a decrease of more and more. So so I can kind of, as this goes like this, and then what happens is the movement doesn't happen too much, but then it kind of hinges, and then bam, like right at the last little tail bit, it then goes the rest of the way. So there's a more and more, and that's kind of, it's a logarithmic polynomial logarithmic function. Logarithmic is probably the better way to say that. And then another way is I can do less and less, whereas a big change here will create, I mean, this will make it swing. A little change rather here makes a big change on the other end. Boom, right? Yeah. So that's another way to do that. So I'm going to stop simulating. That is a crash course in positive and negative. Now, I probably didn't tell you, like, okay, well, what's a nothing? So, well, in a non-relationship, this is what happens in a non-relationship. So I can move A and B up and down, and nothing happens to, there's no correlation between the events that happen in A as it relates to the events that happen in B. They're completely independent of each other. So that is a non-relationship highlighted by this dotted line. Excuse me. Now, I can vary, and there's an interesting capability here. I can make my own process here, and then I can make it do whatever I want on this side. There's another thing that we can do over here is I can hit the settings button, and then I can change this from a model diagram to a static, which is what we are now, to a dynamic. And a dynamic one is what we're going to primarily be using, because a dynamic one allows us to make this temporal. So I can actually simulate and then step through. You can see what it does there. I can simulate and step through different experiments and run those at different times, and then with different variables, and then see what happens. I can step through what's going to happen with one as it relates to the other. Okay, so now let's go ahead and create something that's a little bit more useful for us. That's the basics. Well, let's jump in and actually create a model. So the first thing I want to do is I want to create a simple model that goes into distance, time, and speed. And whenever we talk about distance, speed, time, right, there's a relationship between as the passage of time decreases and the distance increases, then our speed on the output would be higher than it would if those were reversed. So that's the high level, right? So we talk about speed as a function of distance and time, right? So, but how would we model that, right? I mean, I can go look it up and I can get an equation, and then I can go, but I want to have something that visually represents that speed, distance, and time. But I want to take it a little bit further, and then I want to model wind pressure and gas tank, or what, gas that's in the tank, as also an output of this model. So I'm adding a little bit more to it, and then eventually we'll add in a little extra, and then we'll test our model and see if it makes sense, and then see where we go from there. And I'll intentionally break some stuff along the way, just so you can see, because I want you to get comfortable with model validation, model evaluation, and validation. So let's start off by changing some stuff up. I'm gonna make this. Let's go in here and make this distance. So we're gonna say this is distance, and then I'm gonna pull in another one, and I'm gonna call this one speed. I'm sorry, time, not speed. And then I'm gonna call this one speed. and then I'm going to create a relationship between these two, and then I'm going to loop these and bring those over here. So I have a distance to speed, and then a time to speed. So distance to speed, so we double click this. So an increase in distance causes, let's say, an increase about the same. We'll just keep it linear for right now to keep things all simple. So an increase in speed, an increase in distance causes an increase in speed. Speed to increase about the same, so we'll say. And then on time is inverse to speed in this regard. So in other words, as time decreases as it relates to distance, it's not the passage of time, it's the amount of time. So in other words, this is where metrics are very important, right? And our definition of what the variable is very important. This is not the passage of time. This is the time that is covered in that distance. We're creating a relationship between these three elements so that I can get an accurate depiction that as the time increment for a given distance decreases, speed will increase, right? Because that's what I'm trying to model. So so I'm gonna say decrease. Oops, I did the distance should increase about the same. I need to double check. So an increase in time as it causes speed to decrease at about the same. There we go. That's what I'm looking for. Okay. So now actually I have a basic model that I can test out. So remember, right, my hypothesis before I'm going into this is just based on basic physics, right, is that as time, the increment of time decreases as it relates to its relationship to the distance increasing, that will make our speed increase. In other words, if I cover, as an example, if I cover a mile in a minute, then I'm doing 60 miles an hour. But then if I'm covering a mile in half that time, 30 seconds, then I'm doing 120 miles an hour, right? So the idea here is that I'm modeling out that relationship, and now I'm going to hit play and then see if that is true. Now this is conceptual, right? We don't have any specific. Okay, so this is good. This doesn't tell us anything, but we just ran through an experiment, and it shows us that okay, that as time went, speed was in the middle. Okay, but now let's say I keep controlling for distance where we left it here. If I now take time and I decrease the time increment, my speed increases. See what happened? See, my time increases as I decreased my time. If time is passing, right, the time increment that we have has a lot of time has passed, and we chunk it and say, okay, an hour passed, and then I went this distance, well, then my speed decreases, right? But then if I say, oh, wait, distance stays the same, but then I'm decreasing my time increment, then my speed increases. So same with distance, right? If I increase distance, my speed keeps going up and up and up and up and up as my time increment stays low. So this is a good model, for a good basic model of what it is that we're trying to model out. Now, I said we want to do wind pressure, so we're going to add in wind pressure, and then I'm going to create a relationship to wind pressure. So this is the wind pressure on the car. So as you move through the atmosphere, right, as you're driving on the road and as you're making headway, as your speed increases, what happens to pressure? Well, it increases also. But it doesn't just increase a little bit. It actually increases more and more and more. There's like I am not a physicist, so I don't know this for sure, but I imagine that it's almost a logarithmic effect, that as speed increases, the pressure starts to build up and build up and build up and build up and build up to the point where you reach the sound barrier, right? The pressure that you are pushing, you're moving faster than the speed of sound. You hit the sound barrier, and then there's this pressure that builds up. And we could just say pressure in general, but just for our own purposes, for a simple model, we'll keep it wind pressure. So I'm going to say logarithmic. So I'm going to say an increase in speed causes an increase in wind pressure, and I'm going to say more and more. And then it goes up and up and up and up and up and up and up. And then it does it in a logarithmic way. So now I'm going to set these to 0, and then you notice that my speed, so part of my model doesn't make sense already, right? So I'm like, what's going on here? But let's test it out, because this shouldn't be right. A distance of 0 and a time of 0 shouldn't have a speed of in the middle, right? That doesn't make any sense. So this is where everyone needs to be thinking like, okay, well, why is my the initial model made sense, but now this doesn't make sense, right? I need to be in constant model evaluation mode. It's because what I'm trying to do is replicate as faithfully as possible real world physical phenomenon. So it kind of works, right? As distance goes up, and my time is decreasing, my time increment, well, I'll just put it in the middle here. Let's put it right there. So as time, my wind pressure was decreasing. So as time goes up, my speed should go down, and my speed going down should make my wind pressure go down. So if I push this up, these both should start to go down, right? So if I go like this, and that's true. But this is weird, right? I mean, my speed doesn't look right. This part doesn't look right. It doesn't make a lot of sense to me. So one of the things in our model that we can do to clean this up here is it's this averaging thing. It's combining these and making an average. So what I'm going to do is change this to limiting factor, and then that will fix our model. So distance and time are both combined variables using a limiting factor, and that keeps these from creating that average effect that was occurring there. So now this looks like a more comprehensive model. So as my time, I'm going to increment my time just a little bit, and like, see, that makes sense. So if I'm not, it doesn't matter what my time increment goes. If I'm not covering any distance regardless of my time, it means my car's not moving, right? It means that we're not going. We're not making movement. There's no activity. But now I'm going to move this up a little bit. If I add a little distance, then we're going to be making work happen. And that looks about right. That looks good. So this is good. So we're not, so this is good. I'm going to put the distance right in the middle, and then our time. So then now if I want to check for my wind pressure is low. As I increase this, the speed and wind pressure are going to decrease as time increment. Because remember, as my time increment increases and my distance, controlling for distance, and if distance doesn't change and my time increases, it means that my speed is decreasing, and then therefore my pressure on the car, my wind pressure, is decreasing as well. And I can test this by increasing my distance and then decreasing my time slowly. So if I put both of these to the upper limit, and then I slowly start to decrease, my speed's going to come up, and then my wind pressure is going to go up, and then my wind pressure is going to go up, and then my wind pressure is going to go up, and then my wind pressure is going to go up, and I'm going to max it out. So theoretically to a time of 0, which is not possible. But anyway, but this is the idea, is that so far that model checks out. Like, I mean, high level, all the relationships here check out. Now, if we wanted to calculate this like roughly, and we could actually use this as a rough model to calculate the specifics, but we could do that here. We could actually use this to build the equation, right? Because this is actually telling us what we need to know. Now, is it going to be a good equation? I don't know. Again, I'm not a physicist, but we could put the specific variables in here, and we could get Bernoulli's principle, and then we could get all kinds of other fun stuff in here, and really kind of hone in on a working model. But so far, this relationship looks pretty good. So one more thing that I said I wanted to do was create a gas tank. So gas tank. So here's another thing too, which is fun. So speed as it relates to, speed as it relates to gas tank. So it's going to be decreasing, right? And it's going to be more and more, right? It's going to have this more and more effect on it as you kind of, let's get this going in here. All right. And so if I'm going to set these both to this and this, and then, so this is actually our models checking out. So our gas tank, let's say, is full, right? And then because we're not doing any work, we don't have any distance we're covering, and we have a low time increment. Now, if I start to increase this, and our time stays, we control for time. As I increase this, our speed goes up, our wind pressure goes up, and we're using our gas in the tank. So that checks out, right? This is giving us an example of a control system that we are modeling, and it's actually working pretty good. So if I even put this in here, it should still work, right? It should still work. But our time is increasing. As time increases as a function of distance, you can see I get less and less out of it, though. Because as distance increases and as time increases, then that kind of means that I'm not doing anything, right? So I can be, I can have a lot of distance, but if I have a huge time increment, right? So for example, let's say, as an example, let's say, you know, I'm moving a mile, and then in that mile, I take 1,000 years to move, right? Well, I mean, there's a lot of other things that are going to happen, but this is just a hypothetical. But if I take 1,000 years to move a mile, then that means that I'm really not doing, I mean, I'm not working the system really hard. I'm barely moving, right? So those are kind of some of the thought experiments you have to think through when you're doing these type of modeling exercises. But for the most part, so far, it looks pretty good. You know, it's not too bad. Now, there's a cool thing, cool feature here. One last thing I'm going to do before we call it a day for our lab is I'm going to create one more variable, and then I'm going to tie this to a single thing called force. So if people remember their physics, force equals mass times acceleration, which is also a function of what we're kind of doing here. It's not a exact replica because mass and acceleration, I'm inferring mass through the whole model being a car, right? And then acceleration, we are kind of covering that with distance and time here, but it's kind of a little bit of acceleration is a little different, right? Because that's a little different equation. So, but for the idea of that force and wind pressure and all this, it takes gas to make the car run, which as I expend gas, the force should increase, right? There should be a relationship. So where I'm going is there should be a relationship between the amount of gas I burn and an increase. So as I decrease my gas, I should have an increase in wind pressure, right? In an ideal situation, although we're not modeling, we're not controlling for if I'm idle and sitting, right? So, but we're not gonna do that. You could model that in here, right? And then you could put an idle variable in here to control for that. But for us, we're not going to do that. I am going to say that force has an increase on distance, and I'm going to just say about the same. I'm going to keep it simple, and then I'm going to say that force on time is inverse, and I'm going to say the same thing, inverse. And so what this is doing is now I can have one control. I can have one control in my model that then I can account for here without having to play with these two sliders independently. Right now, one control input of force. So if I want to increase my force, like if I want to go up, I now have an ability to model out what high force looks like on the whole system. So here's how I read this, right? High force is a product of a lot of distance covered in a short period of time, which is a lot of speed, which is more wind pressure and less gas in the tank, because it took energy to expend to make that work. And that all checks out. Like I can validate that with a physicist and say, hey, does this make sense, right? And they're going to say yes. Now, is it a precise model? No, it's not. But is it a conceptual model that checks out and is validated? Yes, it is. Because now if I want to say, okay, I want to slowly go down and I say, I want to say low force, like no force, right? Well, then this is telling me that I don't have any distance I'm covering with a maximum amount of time, which means no speed is occurring, and I have no wind pressure, and I have a lot of gas in the tank. So I have a lot of stored kinetic energy, right? I should say potential energy, stored potential energy, not using it, which means my force is low. So yeah, so a force generated is probably the best way to describe that. So this is kind of cool. Now, here's what's really neat about our model here. I can create a graph and I can create a table, new table, right? And then I can run these experiments. I can come over here and I can pull these in, and then I can actually get even more. I can record the movement of all this in Sage Modeler. And then I can actually do different experiments in different ways here, and I can record their output. So in other words, I can do lower, and then I can run the experiment and record it, and then I can go in the middle, and then I can record and run the experiment, and then I can just keep running this. And I can just keep running these different experiments, and then I can take this data that I've been creating here, and I can actually come in here and I can model the time aspect of what it is, time versus distance, as or speed or something like that. And then I can come in here and I can kind of play around with where this is going on our data points. But for us on this Sage Modeler, I now have data that I have created as a result of my simulated model here. And I created not a ton of samples. Actually, not too bad. I got quite a few samples in here. This is kind of cool. So this is all pretty cool. All right, that's all I have. But just as an FYI, there's a lot of good stuff here that you can get from Sage Modeler. That just about covers our lab for today. If you have any questions, do feel free to reach out, and look forward to seeing you next week in our next learning activity.